Hello, I'm Jay Buckley, Technical Training Manager at Honeywell Consumer Products Group. Welcome to the second module of the Autolite Challenge Professional Technician Program. This module will give you an overview of the advanced ignition technologies in today's market. We'll discuss what systems today's automakers are using and give you an idea of what is in development for the future. Let's start with a fairly new technology that's starting to be used by automakers. It's called ion sensing technology. So what exactly is an ion? An ion is a charged atom or molecule. It's charged because the number of electrons does not equal the number of protons in the atom or molecule. An atom can acquire a positive charge or a negative charge depending on whether the number of electrons in an atom is greater than or less than the number of protons in the atom. When an atom is attracted to another atom, because it has an unequal number of electrons and protons, the atom is called an ion. If the atom has more electrons than protons, it is a negative ion or an anion. If it has more protons than electrons, it's a positive ion or cation. This kind of feels like science class all over again. But you've likely heard the term ionization before when talking about ignition systems. If you think about the spark plug in an electrical circuit, the gap between the center wire and side wire is an open circuit. In order for the coil energy to jump that gap, the atoms in the combustion chamber will ionize to the point of plasma. They will conduct electricity and the plug will fire. The ionization sensing ignition is based on the momentary application of a bias voltage across the electrode gap after the ignition event has started the combustion process. The resulting ion current from the bias voltage is proportional to the number of combustion ions occurring. The ion current level and duration can be used to monitor combustion-related phenomenon specific to the cylinder. If you look at this on an oscilloscope, you'll see the following. The signal normally has two peaks. The first peak occurs when the flame is in contact with the spark plug electrodes, and this is due to chemical ionization. The second peak occurs close to the pressure peak, but it correlates directly to the temperature of burned gases, since the signal is due to thermal ionization. The ion signal amplitude increases with speed and load, so idle is the most difficult condition. This is complex stuff. What do the automakers use it for? Well, Autolite engineers use it for pre-ignition detection during initial engine calibration mapping. Saab first used ion sensing in 1988 for cam phase sensing and still uses it for knock detection. Many OEs are using it for knock and misfire detection as well. What other potential does it have? Ion sensing can be a lower cost way to measure and control misfire detection, which is usually done today with a cam and crank sensor correlation. It can also be used to detect knock more accurately than current knock sensors, and it can control air-fuel ratio on cold starts faster than an O2 sensor and at a lower cost. There are many other applications for this type of technology. Most are aimed at more accurate engine controls, as well as the cost savings over multiple electrical sensors. Next up is plasma ignition. What is it? It's defined as the application of electrical voltage to the atomized fuel stream prior to combustion. The long chain of hydrocarbons in the fuel is broken down into smaller parts, allowing for a more complete burn. The net results are better fuel efficiency and less pollution. Plasma ignitions are commonly used today to ignite jet turbine engines. A typical ignition spark in a conventional ignition occurs when the air gap between the center wire and side wire ionizes or becomes conductive. This allows the ignition energy from the coil to jump the gap and create the ignition spark. Typically, this is a high voltage spike with a peak current that rarely exceeds 200 milliamps in energy and is typically much less, around 20 to 30 milliamps. A plasma ignition is a high voltage ignition spark with a very large ignition kernel and peak currents that can exceed 20 to 30 amps. The net energy output of a plasma spark can be much greater than a conventional spark. Let's look at how a plasma ignition works. Essentially, there's a capacitor in between the ignition coil and spark plug. The capacitor stores energy from the coil until the plug gap reaches its ionization point. Then, it will discharge with a larger but shorter duration spark. In fact, most current design plasma ignitions do not use a standard ignition coil. They use high output capacitors instead. So what application does a plasma ignition have in a modern automobile? In today's world, not much really. While it does have tangible benefits as far as the ability to ignite extremely lean mixtures, all the costs of the high voltage components, electronics, cabling, and spark igniters have limited this to mostly high performance racing applications. Because it must use solid copper core wires and non-resistor spark plugs, it also has unsolved issues with radio frequency interference, which can wreak havoc on the PCM in a modern engine. Plasma ignitions have been around for 3 decades, so you can expect to hear more about them as these issues are resolved. So what can we expect to see next, technology-wise? I know you're thinking, lasers? Really? But in today's world, they're already in use on large stationary engines in industrial settings. Most of these engines are fueled with natural gas. Natural gas fuel has ignition challenges related to conventional spark ignitions. Natural gas requires more spark energy to ignite the air-fuel mixture. This results in much shorter spark plug life. Laser ignition systems are being developed right now by many automakers. As you saw in Module 1, with many engines transitioning to direct fuel injection, real estate in the combustion chamber is becoming scarce. The current crop of spark plugs is just too big, and that takes up too much of that valuable space. This is what's driving the development of plugs like the Autolite Revolution HT series, as well as 12mm and even 10mm conventional spark plugs. The need for combustion chamber space for direct injection, multiple valves, and leaner air-fuel ratios are prompting automakers to look for ways to improve ignition. Conventional ignitions have difficulty igniting these ultra-lean air-fuel ratios. A standard spark plug ground electrode of today can quench the spark enough in a lean burn engine to cause misfires. However, a laser ignition can be delivered through thin fiber optic cables to the combustion chamber. A laser spark plug of tomorrow may be a device connected to these thin fiber optic cables that uses mirrors to focus the ignition points to different areas of the combustion chamber. The result is a more complete burn with fewer or no misfires. Another very tangible benefit of a laser-based ignition is its ability to fire different types of biofuels. With constant research on different types of fuels for internal combustion engines, a reliable ignition system will be needed. So, as we've just discussed, technology keeps pushing forward. As technicians, we can never stop learning if we want to stay up to date and have the ability to repair whatever type of engine comes into our shops. Keep this in mind. It takes 1,000 engineers to design and build a modern vehicle and one great technician to fix it. Thank you for your time.